All right, welcome to Unit 5. Unit 5 is going to be all about right triangles, how to find measures of sides on right triangles, how to find measures of angles on right triangles. And so we start today with a very classic theorem pertaining to right triangles. Permit me to show you a right triangle. This red triangle is in fact a right triangle. And you can see it on graph paper, so we can know how big each of these sides are. The side running across the bottom, AB, that side appears to run from 0 to 3. And so sure enough, I can't measure that coordinate distance there, but I can if I pick A and B. And you can surely tell that that is 3. And going from B to C, that distance is clearly 4 because we run from the bottom up to this y value of 4. And then this coordinate distance from A to C, that's 5. And so people have wondered over the years, what is the relationship among those lengths? And so you think, well, is 3 plus 4 equal to 5? Well, that's probably not true, because that would fail the triangle inequality that says any two sides have to add up to be bigger than the third. So 3 plus 4 isn't 5. What is it that is true about those guys? And so we have the thought, and the thought is, I'm not looking at comparing 3 and 4 and 5. I'm looking to compare their squares. I want to take this guy and square it, and I want to take this guy and square it. And if I do that, I get that AB squared plus BC squared is 25. But wait a second. That guy squared is also 25. And so I wonder, is there a relationship? Is it true that this squared plus this squared is the same as that squared? And so I come into a second picture and I say, let's just get some lengths. Just some lengths. That's 9.5 is just a randomly generated triangle. And again, it's hard to tell on the surface what the relationship is among them, but we can certainly take the first guy, square it, and the second guy and square it, and get some number. And we can wonder, is this squared also that number? Is the hypotenuse squared also that number? And it appears to be. Well, is that true? Did I rig that up before you came to the video? Well, I can move this guy up and down. I can move this guy around. And no matter where I stop, it appears that leg squared plus leg squared is the same as hypotenuse squared. And this actually is a very famous theorem that people have been doing for thousands of years. It is called the Pythagorean Theorem. And the Pythagorean Theorem says that in a right triangle, where the legs are A and B, either leg can be A, either leg can be B, if the hypotenuse is C, the length of the hypotenuse is C, we have that A squared plus B squared is C squared. That's the way the Pythagorean theorem goes. To write it out in words, we would say the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. In other words, if I square the hypotenuse, I get the same thing as what I get if I square the legs and add them up. And so that lets us find lengths of sides in a right triangle when two are known and one is unknown. So if I have a leg here and maybe that's got a length of 10 and a leg here and maybe that's got a length of 6 and I'm looking for the hypotenuse, I can say, ooh, this is a right triangle. Pythagorean theorem applies. And since Pythagorean theorem applies, I know a squared plus b squared is c squared. A and b are either leg in either order. So I can say 10 squared plus 6 squared equals, this is the hypotenuse squared. And then it's just up to me to crank that out. 10 squared is 100, 6 squared is 36. And so x is the square root of 136. And then it depends on how your teacher wants you to give that answer. If you're not told to round, you want to leave it as a radical, square root of 136, or if your teacher wants you to round things, we could think of a perfect square that goes into 36, I'm sure, and that would be 4. And how many times does 4 go in? It goes in 34 times. And so we could say that x is 2 times the square root of 34. We could say that. Or if we are told to round to some number of decimal places, we could put radical 136 into our calculator, get a decimal approximation that way. Similarly, if we know the hypotenuse, maybe the hypotenuse is 15, and maybe this little length down here is 6, and I'm looking for that leg. Well, it's a right triangle. When I have all three sides of a right triangle involved in a Pythagorean theorem problem, I know Pythagorean theorem applies. Leg squared plus leg squared is hypotenuse squared. And so I say, ooh, I can do this. 6 squared, that's 36. X squared is x squared. 15 squared is 225. And so by subtracting 36 from both sides, I get that x squared is 189. And so x turns out to be the square root of 189. And I think to myself, are there perfect squares that go in a 189? And I'm pretty sure 9 goes in. So I could write this as square root of 9, square root of 21. And so I've got 3 radical 21. But coach, I forgot all my work with radicals when I was younger. Ooh, that's a bummer. That's a bummer. Because you're going to want to remember all your work with radicals because you're going to want to simplify answers as often as possible. Okay, so here's the thing about the Pythagorean theorem. It works in reverse. We could play everybody's favorite game, is it a right triangle? Is it a right triangle? And so I've got this right triangle, and maybe this is 15, and that's 8, and this is 17, and I want to know, is this a right triangle? Well, if I want to know if it's a right triangle, I use the Pythagorean theorem. A squared plus b squared is c squared. C is always the biggest side. It's the hypotenuse. And I use my calculator. I want to know, is that a right triangle? Is 64 plus 225 equal to 289? And the answer is yes. Yes, it is. That is a right triangle because the Pythagorean theorem works. But what happens 6, 7, 9? Well, I have this funny feeling just by tone of voice that this is probably not a right triangle. And so I ask myself, what is the relationship between 36, 49, and 81? Well, the left side, this comes darn close. The left side is 85, and the right side is 81. 85 is bigger than 81. So this is not a right triangle. In fact, it's an acute triangle. If the sum of the squares of the legs is bigger than the square of the hypotenuse, if the c squared is less than the rest, I've got an acute triangle, not a right triangle. Similarly, if I were to take some triangle like so and say maybe 4, 5, 8. That seems reasonable. Does that seem reasonable? That seems reasonable. What color haven't I used yet? Green. 4 squared plus 5 squared, is it or is it not equal to 8 squared? Well, 16 plus 25, is it or is it not equal to 64? Well, the left side is 41 and the right side is 64. In this case, the 8 squared totally devours the 4 squared plus 5 squared. And since the 8 squared is bigger, we've got an obtuse triangle. So the Pythagorean theorem works both ways. If we know we've got a right triangle, then we can use Pythagorean theorem to find a missing side. If we don't know if we have a right triangle, we can use the Pythagorean theorem to find out what kind of triangle we have. Side note, there are of particular interest to us in the mathy world Pythagorean triples. There are certain right triangles that folks like me love to use all the time. One we've already seen, and that is the 3, 4, 5 right triangle. 3, 4, 5 works because 3 squared plus 4 squared is 5 squared. We've already covered that. So 3, 4, 5 is a right triangle, but so are all of its multiples. So if I wanted to make this just a wee bit bigger and multiply everybody by 2, I would say, okay, instantly I know that that's a right triangle because every multiple of 3, 4, 5 is a right triangle. Similarly, if I got a lot bigger and I made 150 and 200 and 250, that is a multiple of the 3, 4, 5. That just takes the 3, 4, 5 and multiplies every side by 50. And so everything that's a multiple of a 3, 4, 5 is a right triangle. There are other Pythagorean triples of which we are fond, the 5, 12, 13 right triangle, because 5 squared plus 12 squared is 13 squared. That works. The 8, 15, 17 right triangle, because 8 squared plus 15 squared is 17 squared. So these are some things you should be looking for when you see the 3 sides of a right triangle are all whole numbers. That's a nice triple to stick in your toolbox and say, I'm going to be looking for multiples of those things because my teachers love it when the answer works out as a whole number, and so they're going to use those things over and over again. So that's the Pythagorean theorem on display. If you have a right triangle, the 3 sides are related by a squared plus b squared equals c squared. And if you don't know if you have a right triangle, you can find out what kind of triangle you have by trying the Pythagorean theorem and seeing if it works. All right, that's our lesson. We'll see you tomorrow.